Current section. There we go. Okay. All right, my friends, does anyone have any questions from this review? And then we'll move on to other ones. Now, granted, we have not completely finished the unit yet, right? So there might be things where I'm like, no, we need to cover this. Yes. 58. And I'm hoping I got the right version of this thing printed, so let me know if your 58 is the same as my 58. Test is on Thursday. No, I might give you a practice quiz, but, right? Okay. An aqueous solution contains sodium, nickel, zinc 2+, and copper. Which ions can be extracted by electrolysis of the solution? So what that means is which of these can we turn into the solid? Can we extract sodium? Can we extract nickel? Can we extract zinc?
We acknowledge and thank the Coast Salish Nations of 1.02 Squamish on this traditional territory from Peach Land. Today's date is Monday, January 12th. Phone Free Lunch. The Health and Wellness Council is back with an exciting phone free lunch event on January 16th. This is a space for you to hang out with friends, connect with others, and play board games without yourself. Enjoy our free hot chocolate and chocolate chip cookies while taking a moment to step away from your life and join us. Come join us for a fun, relaxing lunch. Burnaby School District counts career, education, and social. January 14th at 8 p.m. at Burnaby Central. Students are invited to join us in exploring the 50+ industry training program partnership with school secondary institutions and community partners. Speak to industry partners, specialized teachers in the program, and find out more.
Yes. Right there.
Grade 11 is developing. The Career Center has many volunteering opportunities for work experience hours. Make sure you get your paperwork from the Career Center before you get if the staff wishes to talk to you or just want to meet people, we have a place for you. Social Business Health is hosting a speech friendly event on Tuesday, January 13th in room 210. Come and meet friends and get a free snack and have a great time. Everyone is welcome. You can't waste a few minutes. There's going to be a youth book drive this week on Wednesday and Thursday at lunch in the Commons. So everyone please bring your used books.
So which of these ions
Just a reminder
are able to be reduced?
CLC 12 capstone preparation meetings have started this week in the Career Center. If you can't remember which one, drop by the Career Center anytime to check it out. Thanks and have a great day.
Which of these can be reduced into their metal in solution? That's what it asks, if you can extract them from solution by electrolysis. And how do you know? What should you be thinking about if you read this bit? You should be thinking about water. So which ones can you extract? Can you extract copper? Yes. Why? It has a higher reduction potential than water. Can you extract nickel? Yes, because it has a higher reduction potential than water. Can you extract zinc? Yes, because it is within the overpotential bracket. I don't know if I talked about it in these terms with you last day. I certainly did with the other block. I call it the magic bracket because, quite frankly, I don't understand the overpotential effect, but I do understand that whatever is within the bracket will win over water. Yes? So if anything is within the magic bracket, it will win over water. In other words, that reduction will happen before that of water. It has a higher reduction potential than that of water. Is good? How about sodium? No, it has a lower reduction potential than water. All right. What else we got? 50. Consider the following redox reaction. The reducing agent, so we need the thing that is getting oxidized. And one thing I'm going to do is I'm going to point out that, oh no, never mind, I'm wrong. So manganese, I'm just going to guess that it's manganese because I noticed that manganese has a whole crap ton of oxygens on it. Yes? And over here we have MnSO4. What is the oxidation number of manganese here? Tell your partner. What's the charge of SO4? 2 minus. So what's the oxidation number of manganese? 2 plus. So what is the oxidation number of manganese over here? We have a +1 and we have a -8, and that's all going to equal 0. That means manganese has to be +7. Did manganese get oxidized? Yes. Now, what's the other thing that's getting oxidized or reduced? It's not the sulfate, because sulfate stays as sulfate, right? It hasn't changed. It's still SO4 2 minus from side to side. So I'm guessing that, and K is just K plus, can't be anything else. It's an alkali metal. So I'm guessing carbon. And carbon here is, what, 4 plus? And over here, carbon, I've got -8, I got +2. That is, what's -8 and positive? That's -6, so this is +3, I think. Yeah, +3. So it went from 4 to 3, so it got reduced. Okay, so the reducing agent is MnSO4. Demi, you had a question. Sorry? 9? The copper used in smelters contains many impurities. Which of the following procedures is used to produce almost pure copper? We have not covered this yet. Shall we cover it now? Let's do it. Okay. Oh, do I not have it here? Oh. Okay, we're just going to have to go notes. Because apparently I don't have it here. What the hell? So bizarre. That's okay. Add a page. There we go. Yeah, I missed putting applications of electrolysis in your notes. That was not clever. So you need some place to take notes. There is lots of paper at the back if you don't have any. Okay, so there's this type of copper called pig copper. And pig copper is mostly copper, but with impurities. And those impurities can include zinc, lead, silver, gold, platinum. Electrorefining, purifying a metal by electrolysis. So what you got is you've got this block of copper, yeah. But in there, there's a little bit of zinc, there's a little bit of lead, a little bit of silver, a little bit of gold. Yes? And you're like, I just want the copper. I do not want the silver. I do not want the gold. I do not want the lead. I do not want the whatever the other one was that I forgot to mention. Okay, so what we're going to do is we are going to attach this piece of pig copper to an electrode. And I would like to remove these, or sorry, to a wire. I would like to remove these ions. How could I remove them? What electrolytic process, what half reaction would remove these from the copper? Sorry? Oxidation. And it will remove metals one by one. From the pig copper.
What does it mean by
one by one? Which one will go first? Which one will oxidize first? Yes, you're absolutely correct. The strongest reducing agent, the one with the highest what? Oxidation potential. So, who is that? Who will go first? Yep. So first, zinc. And what is the oxidation potential for that?
0.6.
Positive or negative? Excellent. Who goes second? Tell your partner who goes second. Who goes second? Lead. Because lead has an oxidation potential of negative 0.13 volts. All right. Oh, positive? Okay. Who goes third? Copper goes third. Oh, we're going to get there. Just hold on. We're going to finish writing this line. Then we're going to get to that. We're going. Yeah. Which, does it go to copper 1 or does it go to copper 2? Copper 2. Remember with the copper, it's always going to go between copper 0 and copper 2 unless things are really weird. Okay? And I don't think they'll ever be really weird. I think it's always, because it's always got the best potential. Okay?
That's going to be negative.
Negative 0.34 volts. Okay, so this is lovely. So we have removed the zinc, we've removed the lead. We would like copper metal by itself, but unfortunately at this point, what's happening to the copper? It's getting oxidized. So now we have copper 2 plus, but we would like it to be copper metal. So we start reducing it. Yes.
How do you figure out like?
Oh, you just turn it on and let it go. It'll just do it on its own. And I'll show you why in a moment, okay? How do I know what? Oh, hold on. Just wait. No. Just hold on. Hold on. Hold on. So now we're going to draw a little cell. Okay? So we have our pig copper, which also has zinc and lead and Au and Ag. Oh, and platinum. Oh. 1, 2, 3, 4, 5. I forgot one before. PT. There we go. Okay. Ag. Now, so there's our electrode. We're going to attach it to our power supply. And then we need it attached to another electrode, which is going to be made of something. It's just settle down. Relax. We'll get there. I cannot write everything so fast. Like it's impossible. I don't know why this is in the beaker, but that's okay. There we go. Okay. DC. Where do we want the positive terminal of the DC power supply? I want you to think about what electrode is this? This electrode is the? What are we wanting to happen? We're wanting everything to oxidize. So it is the anode. That means our other is the cathode, which means which direction are electrons going? They're going from the left to the right. Right to left. Sorry, I have a tendency to say left and right backwards. I'm very, very sorry. My brain does not do well. And so where does the positive terminal of the DC, is it on the left or the right of the DC? If I put the positive terminal here, what will it do to the electrons? The positive terminal would attract them, which means the electrons would be going the other way. So we want the positive terminal to be over here, and we want the negative terminal to be over here. Now, first thing that comes off is zinc 2 plus. Second thing that comes off is lead 2 plus. And the third thing that comes off is copper 2 plus. Now we want copper to go and get reduced. And just chill. I know you've got questions. We can only do one thing at a time. What should we make the cathode out of? What material should we make it out of? Sorry? We should make it out of copper. Because you want purified copper, yes? What would you want your pure copper to attach to? Copper. Yes? So our Cu2 plus is going to go over here. So over here we have Cu going to Cu2 plus 2 electrons. Well, first we had zinc going to zinc 2 plus 2 electrons. Then we had lead going to lead 2 plus 2 electrons. Then over at our cathode, we have Cu2 plus 2 electrons.
Like DC stands for direct.
Direct current. Why are the zinc and the lead not getting reduced? Tell your partners. Yes, they are there.
Yeah, well, yeah, it was kind of
What's going on? How do we know? Yeah, copper has the highest reduction potential. Yes? So it will be preferentially reduced. Over zinc, 2 plus, and lead, 2 plus. What is the reduction potential of copper? .34, positive. I didn't have room to write that. Positive 0.34. What is the reduction potential of, actually, maybe I should do it this way. That would be so much more clever. There, it all fits. What is the reduction potential of zinc? Negative 0.76 volts, and lead is
negative
0.13 volts. So, winner, winner, chicken dinner. Copper is preferentially reduced. What happens to the gold and the silver and the platinum? Now remember, this thing is mostly copper. Yes, our pig copper is mostly copper. Well, what's happening to our mainly copper anode as time progresses? It's shrinking. And you can imagine that if I were the copper electrode and these scissors were some silver, yes? And if, okay, I'm copper, yes. This is silver. And there's silver like in the copper, yes. And as this copper gets reduced and goes off into solution, what happens to the silver? It just falls off. Yes, because there's nothing holding it there anymore. Did you have a question? The other electrode, what?
The copper
Does it smasi? What are you saying? You need to speak up.
Masterpiece.
Does the mass increase? Yes.
So we're getting copper dose.
Yeah. So basically what's happening is we are taking the copper out of here. Copper goes out, and then the copper goes on. So the silver and the gold and the platinum will just fall down as the copper around them goes out into solution. The zinc and the lead are just ions floating around in. They're just hanging out, dissolved. Yes.
Wait, so do they just like float around or is it?
The silver, the gold, and the platinum, these are all solids. And they literally just fall as solids to the bottom of the container as the copper around them goes into solution.
So they don't do anything?
No.
Wait, Spanish?
That's fun. Do they dissolve as ions?
No. They just fall to the bottom as solids. Yes? Right? Did this turn into an ion?
No.
Or did it just fall? Yes, Tony.
So when the copper goes from the anode, what's happening? Like when the anode is it gets oxidized, and then when it goes to the cathode to like I guess like precipitate onto the pure copper, is that like a reduction?
That's a reduction, yes. So we have our two half reactions are the opposite of one another. Okay, we're going to summarize that down below in just a minute, but those are our two half reactions. Did we need the zinc and the lead to come out first before the copper would start coming out? Yes, but this is the main reaction that's taking place. So, let's just also mention what happens to the Zn2 plus. Yes.
The solution in water or
Well, we're going to get there.
sign?
We'll get there. Can we finish an idea first? What happens to the zinc and the lead 2 plus?
Oh.
Oh,
What do they do? Hmm? They stay in solution. They just float around. Yeah, they do nothing.
No, the only thing that goes
like so solution like
Yep. Copper itself is toxic too.
I felt like solid copper was like just like I thought it was
Solid copper is okay, but copper 2 plus is a different beast.
Oh, or like a lot of the
A lot of them are not good. I mean, iron's good because you need it because, like, you know, for your blood and stuff, right? And if you were an octopus, I think they have copper in their blood instead of iron. I think. I could be wrong, but there's some kind of biological organism that uses copper instead of iron. Yeah.
That's what the concept is, and that's how you get money.
Boy, I remember. Where's she go? Her hands like, and then about. Like, for the time, like, that's like, oh my god, that's different. No, like, that's the invasion.
Okay.
Like, it's great for Apple.
What electrolyte should we use in this cell? What do we mean when we say electrolyte? This is our salt. And your salt can either be, it can be in one state or the other state. What are the two states the salt could be in? It could be aqueous or not solid. It won't be an electrolyte if it's solid. Or liquid. So first of all, no, there's no gas. Are we going to choose aqueous or liquid for this cell? Yeah, we're going to choose aqueous, right? Like, we got all kinds of ions that need to be dissolved in there, yes? So we're going to choose aqueous, besides which molten salt would melt our copper electrodes. That's no good. Okay, so we've got aqueous here. What salt do we want to choose? Yes, a copper one, because you want the stuff plating onto the pure copper to be copper. You don't want anything else in there getting in the way, doing nasty things, right? You want it to be copper. Who would be a suitable anion? NO3 minus or SO42 minus? And for copper 2 plus, I would go with copper sulfate because it's a really common salt, but you are not expected to necessarily know that. Okay? Okay, now if you want to read more about that, you can, oh, actually no, we need to write our reaction at the anode, write our reaction at the cathode, and we're going to calculate the E naught. Let's do our overall reaction. So what is the anode reaction? Yes, there are, but what's the important one? Copper. Cu what? Solid. Goes to Cu2 plus 2 electrons. And our oxidation potential is negative 0.34 volts. What's our cathode reaction?
Opposite of that.
The opposite of that, we got Cu2 plus 2 electrons goes to Cu S. Now, I'm going to put a couple little things on here. On our anode reaction, this is our impure copper. And in our cathode reaction, this is our pure copper. Yes? And our reduction potential is positive 0.34 volts. What's our overall reaction? Cu, solid, plus Cu2 plus, goes to Cu2 plus Cu, but this one is impure, and this one is pure. And I guess I should write that that is a solid. And what is our cell voltage? Is 0. You don't have to write the Cu2 plus. It's just there to remind you that it's going in and coming out and whatever. I don't know. Yeah? Okay. Yes.
For the electrolyte, how do you, or like, when do you know to like use the liquid instead of the?
Only use the liquid if you're trying to get out something that cannot get out with water, like something with a reduction potential lower than water. So those would be that would be
Everything other than the over.
everything other than the over potential that's below water. So manganese, aluminum. Whoa, that was supposed to be a highlight. So you would use molten for all of these guys. Yeah?
That's when you use water.
That's when you do not use water.
Oh, that's when you don't.
Because they will not get reduced. Water will get reduced instead. Yes? Yeah.
Use water.
Okay. So that is one application of electrolysis. Shall we do the second one while we're here?
Can you go back up to the diagram?
Of course.
How many applications?
2.
I need to look at this thing.
And this is also in Hebden on page 245.
This but so the zinc and the lead move to the copper as well.
They move there, they just don't get reduced. But cations always migrate towards the cathode. So, yeah. Okay? All right.
So this down.
Electroplating.
That
Design an electrolytic cell electrolytic cell to electroplate a copper medallion. No! Example.
Oh, I remember now.
With nickel metal.
like a different. So you know, like metals or something. So they'll just add them to the-
Okay, so here is our nickel medallion. What else do we need? We need copper. Where do we need copper? Right now, I've got a nickel medallion and I have a wire. What else do we need in our cell?
Solution.
We need a solution. Before I have a solution, what do I need? I need a beaker. Okay. What else do I need? Another beaker? Over here?
Yeah. How do you use only one?
No.
One beaker. It's electrolysis, yeah? Electrolytic cells need only one beaker because there's no spontaneous process that could happen without passing through the wire. What do we need in an electrolytic cell? Yes? A copper. Oh, the medallion is made of copper, not nickel. Thank you. I need nickel metal as well. Where would I put my nickel metal? As an electrode. What else do I need? Yes. I need a battery. Okay. So we're going to put it up here. Now we have to decide who do we want to be the cathode and who should be the anode.
Hold on. Basically, want nickel plate, so we have a line. We want the reduction here. We want reduction here. So we want.
Wait, Dorothy.
Yeah.
So there's 3 questions for you. Who should be the cathode? Who should be the anode? What electrolyte should you use?
Electrons will always be out. Right.
Yes. That's okay. Does what? Does the cathode gain mass? Everybody, does the cathode gain mass? Yes. The medallion should be the cathode because you want nickel to become what? Nickel 2 plus, you want it to become what on the medallion? You want it to be reduced. You want nickel to turn into nickel solid, which means, right, this is our plating process where we have nickel forming on the outside of our copper medallion. And that process is that oxidation or reduction. That is reduction. Therefore, the copper medallion must be the cathode. Okay, so and if it is the cathode, and the nickel is the anode, you can decide if you just want to throw your battery in right now. I usually find it easier to put my electrons in first because my brain just works better that way. Like if I know where my electrons are going, I know which terminal should be positive and which one should be negative. So which direction are my electrons going? Right to left or left to right? They're going from right to left. So my electrons are going this way, which means if I've got a battery, where should my positive terminal be? On the left or on the right? The positive terminal should be on the right, and the negative terminal should be on the left. Okay? What are we missing from this cell? We're missing electrolyte. What should we have as our electrolyte? We should have nickel in there, yes? Because we want nickel 2+. What would be a good choice to put nickel with? Sulfate.
When the electrolyte is right?
Yes. Just because that's what we usually choose. Don't use sulfate if it's... Don't use sulfate if it is calcium or barium or one of the ones that it's low solubility with. Silver, calcium, strontium, barium, lead. Yes? But other than that, you can use sulfate. And sulfate's a good choice because it is extremely electrically inactive. Yes? Okay. So what is our reaction at the cathode? And what is our half reaction at the anode? By the way, electroplating, electrorefining, super duper written response questions. So what's our half reaction at the cathode? Cu what? Cu solid? Is that what's happening at the cathode? We're taking Cu solid and turning it into something else? No. The Cu is the cathode, but are we turning it into anything? No. What is happening at the cathode? Nickel 2 plus is doing what? It is gaining 2 electrons and becoming nickel solid. What is happening at the anode? Sorry? The nickel solid is getting oxidized. Yeah, and this is why it's important that your anode be made out of nickel, because otherwise you're going to run out of nickel. Yes? Like if you had an inert anode, it could work, but you'd have to keep dumping copper sulfate into the solution to replace it once you run out. Whereas if you have a nickel anode, it will just replenish the nickel as the reaction proceeds. Does that make sense? Yeah, okay. So that replenishes the nickel 2 plus concentration. And our overall reaction, oh gosh, is nickel solid plus nickel 2 plus goes to nickel 2 plus nickel solid. And our E naught cell is 0 volts. So basically you plug this thing into DC and you just turn it on just the slightest amount. So you only need like just greater than 0 volts to run this cell. Is good?
When you not right it.
Yeah. Yep. Yes. Like, do we want like the salt to undergo hydrolysis? Not really, no. I mean, sulfate will a little bit, but not a lot. No, don't worry about it. Just put that in a different box in your head. Okay?
Okay.
Yes? Okay. Good. Are we good with that? X, yes. The nickel and the copper can spontaneously react. So you mean like nickel grabbing electrons from the copper? Let's take a look. But we are pumping electrons into the copper. Let's just go take a quick look. Hang on. I don't even need to take a quick look. What am I doing? Let's go back here. So, the reduction potential of nickel is negative 0.26. The oxidation potential of copper is positive 0.34 volts. So what you're saying is, then why are we just not getting a spontaneous reaction? Yes, okay. And the reason is our battery is pushing electrons into copper. Can copper lose electrons when we are throwing electrons into it? No, and that's why. You wouldn't want this just to sit here. You would want to turn it on and then put it in the water. Yes? So you would want to turn this on and then put the copper into the solution.
So if we don't have the battery?
If you don't have the battery, then you've got a problem. Yeah. Yeah? So, yes, this would cause a spontaneous reaction. These would react spontaneously. But the battery pumps electrons into Cu solid, preventing its oxidation. Therefore, it is important to turn on the DC power supply or attach the battery before placing the electrodes in the solution. So yeah, if you were to put them in there beforehand, before turning it on or before attaching it to a battery, that process would start happening and your copper medallion would start to oxidize. Yeah, very good point. Thank you for bringing that up.
Like, out a little bit.
Like that?
Yeah.
Yes. Will we run out of nickel? No, because we've got the anode turning into. Yeah, but I mean, how much nickel do you need on that medallion before it's done? And you say, okay, I'm done, take it out. Probably not very much. So as long as you've got a decent sized anode, you'll be fine. Yeah? Shall we go back to question 9 now?
This is all for question.
No, it's not all for question 9, but copper in smelters contains many impurities. Oh, look, that's our pig copper. Which of the following procedures is used to produce almost pure copper? Is the impure copper melted and centrifuged? No. Is the impure copper boiled and the pure copper condensed? No. So we are looking at only 2 reasonable answers here. Okay, the other 2 are kind of silly. Is the impure the cathode of an electrolytic cell and the pure copper the anode? Or is the impure copper the anode and the pure copper forms on the cathode? It is D. Yes? That was an excellent question, Demi. Thank you for bringing that one up. Do we have other questions? Yes. 127, question 5. What section is that? The what voltage must be applied to a 1 molar solution of HCl? Yes. Okay, so we have H plus, we have Cl minus, and we have water. And the hydrogen can get reduced. Yeah, this is very much like last class. Cl minus is the oxidation potential is negative 1.36. Water's reduction potential is negative 0.41. So out of our two reduction potentials, hydrogen is going to be preferentially reduced. But water also has an oxidation potential. But chloride is in the magic bracket. So the overpotential effect causes chloride to be preferentially oxidized. So we are looking at E naught cell is equal to the reduction potential plus the oxidation potential. And so that is 0 plus negative 1.36 volts, which is negative 1.36 volts. So we would need to apply positive 1.36 volts. And our products at the anode and the cathode, hydrogen is being reduced. So at the cathode, we would have H plus plus an electron goes to, except for it's got to be H2. Yes. So we need 2 of those and 2 of those. Yeah. So H2 is produced at the cathode, and at the anode, we've got Cl minus, 2 of them producing Cl2 gas plus 2 electrons. Is good? Cool. Yes. Number 3 here. 3E. Okay. 3E, we have K2SO4. All right, so we have in our beaker K plus, which has a reduction potential of negative 2.93. We have SO42 minus, which has an oxidation potential of negative 2.01. Sulfate does not have a reduction potential because it would need to be acidified. Okay. And so our only other thing is water. Okay. And it has both an oxidation potential and a reduction potential. So that means that out of all of these substances, water is the winner for both oxidation and reduction. Yes? So we would look at our the reduction of water. So at the cathode, we would have 2H2O plus 2 electrons goes to H2 plus 2OH minus 10 to the negative 7 molar. At our anode, we would have the oxidation of water, which is again in the gray bar. So we would have H2O goes to 1/2 O2 plus 2H plus 10 to the negative 7 molar plus 2 electrons. And the oxidation potential for that would be negative 0.82 volts. And so our overall reaction then would be 3 water. The electrons cancel out. Okay, we end up getting H2. Now, we put 2OH and 2H together. What do we get? We get water, so we get 2 waters. And so that means, oh, and we also have 1/2 O2. So that means that we can cancel out 2 of the waters and just leave ourselves with 1 water. So we end up with H2O goes to H2 plus 1/2 O2. Sorry? Like something else go the opposite process. Yes, we've seen that where the copper is getting oxidized and reduced. I think is that what you're asking about? Yeah, so yes. Yeah. Anything else? Yes.
Like on this page, the number 3.
3G.
I'm not, like, I don't know what that is that counts.
Oh,
One is like a.
sure.
What is that? Like, it's the
3G, the bottom one is the answer because the reaction, for, well, you would have H2 and FeOH2, right? Because these two then make up.
Oh.
Yes. So it's going to be H2 and FeOH2.
And those two
Then combine. Yeah. Mm. Anything else? Yes.
On still the electroplating.
Yeah.
And copper, well, bonding is perhaps nickel, then and copper also be the cathode, will be the cathode. If this reaction spontaneously.
Sorry, if the copper would spontaneously react with the nickel.
And copper will be.
No, it's the cathode because we've attached it to a battery.
But if it's spontaneously.
If it spontaneously reacts, well, then you don't have a cathode and an anode because you don't have a cell anymore.
It's now the cathode.
The copper would then be the.
What's that now?
It's just there's no cell because the cell needs a wire. It needs pathway for electrons to flow through. Yeah, but what's it doing? Are the electrons flowing through the wire? Like if you turn off the battery, if that wire is there, is it doing anything?
So if we had to today, this would be separate.
For it to be a cell, an electrochemical cell, yes. Otherwise, you just have a redox reaction. You just have a spontaneous redox reaction that is not providing any useful power because it's not forcing the electrons, it's not running the electrons through the wire. Yeah. So galvanic cells push electrons through a wire themselves, and electrolytic cells have the electrons pushed through a wire by a galvanic cell. Yeah. Any other questions? Yes. Okay. I would say at this point, continue with your review. If you want some practice on applications of electrolytic cells, Hebden pages 244. Actually, 243 through 246. And how many of you would like the overall AP multiple choice review printed out for you? Hand up high if you would like one. 1, 2, 3, 4. Just 4 on this side of the room. Nobody else? Excellent. 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and I'm assuming Tony. 15. Okay. 15 MCQ. Excellent. Thank you.
Question.
Keep working on your review.
6.2.
Yes. Yes.
It's just like these questions. I know it's simple, but like I'm getting like the wrong answer. I'm wondering.
Okay.
It's just simple stoic, right?
Yeah. So we have.
And they Oh. They want to have impure.
What?
Okay.
People's that the what's your name?
Okay.
How is it true with freedom? Okay, here's what your categories here, right? And there's 1, 2, 3. So it's 4 degrees of freedom.
You will have a second visit like later.
No, it's
Oh, I guess.
You're not gonna have like.
So this is our.
This is it.
So that. Yeah.
Yes. For chemical, yeah, because it's non-spontaneous, so that's why it's going out now.
It should be one line that.
That would be the spontaneous reaction. If I were just to place a piece of zinc with some, yeah, if I put a piece of zinc with a bromide ion, it won't react. Right, because we don't have Br, right? So, yeah.
So also, we have the.
You do look at the left, yeah, you look at the left and what's it.
It's not like.
Yeah, the electrons may or may not, yeah.
Okay, yeah, okay, thank you.
You're welcome.
Alright, watch me drop like a 6. Watch me drop like that.
I'm talking about this.
I don't understand. This is perfect.
Okay, okay, so this is our reaction, yes?
Yes, I got that.
Okay, so you get H2, do you? Yes?
So. Yeah, so basically, Mr. Leon doesn't care.
Then you make iron 2 plus hydroxide, which are low solubility.
So that.
So instead of staying aqueous, you precipitate.
8 out of 12.
It's the other product.
Okay, to be fair, the first one I picked is
Reactants.
That's good.
Because it's in solution. Yes. What happens with water? Some of it gets used, but most of it is solid.
Yeah, so there's unit 8 and 9, right? And Mr. Leon did the right stuff. Unit 8 is like 5 to 1.
How come there's hydroxide? It's not in the reactants. This is a product undergoing a second reaction. It's step 1 and step 2. There we go. Step 1, step 2. Yeah. What about this?
I was trying to combine step one and step two. It makes sense.
Well, I was like, oh, you just can select here. To make sure that we get.
Okay. Yeah? Yeah.
Yes.
This is more of a physics question, but obviously they're possible. So is the current state of
I don't understand ACA. You structure physics. You need to talk to a physics teacher. There is Ms. Campbell, who is a physics. I will answer that question. Or sorry, 313. You say all the values in 311. Oh, thinking of more. She usually doesn't. They should. Like that one, like I thought it was just me. It was my issue. Like it's hard to. Okay. One of my was. Or like she's pretty good. I think you're shy. I think you're really shy.
Yeah, just do that.
The one I We're not, we haven't started. But I will commit to start. Yeah, was it? It's long-ish, but it's not like hard.
That's what
You know what I mean? Like, yeah, it's
Application.
Yeah. I love college.
Like there's strong fishes.
No, but now you gotta go through.
Notes like that.
So that's what you have. It's like, everything that we'll do. Thursday.
Okay.
Yeah,
yeah, I'll be
Okay. And it's not. Read it up. You're welcome.
It has validity. Huh? Oh, well, I put it on personal.
Bye.
So,
What is the point? Because I don't distinguish between workflows and workout clothes. My mom doesn't really care. She's like, as long as you get like I just so we have it. So I bet if I have this on chromium here, I'm like, what are they here? Like, holy curious. Yeah. And we have filled with I sort of like sorry, 0.8. And we had 3.74, so the thing was 2 plus 0.74 is. So, I don't know how I this.
for this one particularly, I was very.
Okay, so you go from this is one example where you don't use 0.34.
Oh, that's what I was wondering.
That's why I said not 100% of the time. If you're going from copper 1 to copper 2, so and going from Fe3 plus to Fe2 plus, yes. So I've got plus 0.77 and plus 0.15, so 0.77 minus 0.15. Yeah, so it's either 0.77 minus 0.15 or 0.77 plus negative. What's it quiz about? Everything in sections 5.1 and 5.2 A, B, C, D.
And then with this one, we got, silicon create. So much fun. Right, so you've got a acidified nitrate, which is here, right? There's also one here, but this one produces water and also gases. Yeah.
You have the type 3 cells, huh?
We haven't done what?
Type 3 cells.
Yes, we have.
What-
They're the ones that have electrodes, so
Oh, you
electroplating,
refining.
yeah.
Okay, that's like,
And corrosion.
yeah, that's what I'm.
Corrosion tomorrow.
I'll be back. Something isn't that big. See you in. I'm not even kidding. You should ask Joki and Brian. I just went like, she's gonna say see you in O3. Is that what she said? I wasn't in the classroom.
See you on Chris and see you at the floor.
But you could use CO-NO3, right?
Could you see on?
Yes.
It's not as common of a compound, but yeah.
Then I was like, about to enter the class and be like, wouldn't both of these hydrolyze and wouldn't that make a difference in some way or the other? You're feeling cold.
Yes, I'm
You
chilly.
you should have a hot.
No, just gonna go eat my lunch and drink my warm tea. Do you have any more questions though before I go? No? Okay.
Let's come back tomorrow.
Okay.
I have to.
Okie dokie. Oh, hungry.
Hours of studying just to realize that everything was a basic concept.
It's true.
I-
Everything is kind of.
I can see my teachers are stressed too because my teacher messed up a easy concept.
Right?
Yeah.
Yeah, like yesterday, I realized that I needed to make up new electrorefining so that they're smaller, so they'll fit in the time space. So I had to do it from scratch. So I spent 9 hours doing that. That was super fun. Yeah, because what I do is I go through and I wanted to make sure I had like 8 tests that are shorter, and that just means that from now on I'm going to make my electrochem test shorter.
You like spend 1 and 4 hours or something.
Well, the thing is, mostly what I'm doing is I'm working with my spreadsheet that has all the questions with all their percentages and their prescribed learning outcome. And then I go through and I make sure that every test has every prescribed learning outcome, and I make sure that every test averages out to 65.9%.
That's the average rate of passing.
For those questions, yes.
Oh, okay. That means I'm not as bad at it.
No, on the acid-base test, the average exam on that exam is 62%. So, yeah.
So my thesis.
No, it's not that bad.
And then once we get it to
Okay, so you would have 1S3, 2S3, 2S6, 3S2, 3S6, 4S2, 3D, the D's lag 1 behind. So this would be 3D10. And then 4, we go back to 4, 4, 3. Yeah, those are the ones. Yeah. They're fine. Sorry, no, for P one. This is our P block. No, that's in.
Would Arturo Silva come to the office? Arturo Silva, please come to the office.
We have. Yeah, no, it's 3D10 forestry for 41. 41 is in the big block. Yeah. I don't know. No, the D block ends earlier, yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Otherwise, there's 11. That's why you're so confused. Yes.
Special class.
Huh?
Like a special.
Review?
I don't know. It's like.
Nobody shows up. Yeah, sometimes during class, I'll be like, oh, we're running a review for 8. And then they're running. Yeah. Oh, sure, it's good, right? I'm not gonna describe it. I should tell you the last one. It's like, now, that's really different. Yeah, you're like, oh, what about that? Yeah. I love this guy. Emilio, area to the office. Emilio, area to the office. Emilio, area, please come to the office for an important message. Emilio, area, please come to the office for an important message. Wait, I just started watching. They're very young though. Oh my god, whatever. Until I go, I think oh, it's no, we should. In this, she goes, well, not that she takes her trolley from the office. Have you finished it? Or? No, yeah. Just go like you're on 3/4 or the class during one grade period. Okay, I just not going to. I go. Yeah.
Oh, yeah, I didn't talk to you. Yeah, only you're allowed to work on it.
But I never go. I want to.
Oh, yeah. But it's not that big, but. I'm happy to talk to you. Very talk to you. But I had 15 listening times. Now, only 13. And tomorrow's gonna be 12. And then, let's say, okay, so. No. About $1, right? Let me see that. 360. I don't have to. Oh, it's my coffee. I look 5 minutes for it on the school, bro. Like, got shot from milk. I didn't get milk from the kitchen. It's over 30 minutes to sit in the shower. I sit in the front back. It's not one. But it's not like shower. I put on some top here. You know my oats? No, give something to Sean. See how you subscribe it. Oh, right. I just have a date. I didn't play this soccer thing. It had like the yes, not. Are playing time? Really?
What?
I
Yeah.
One, put it up, right?
Oh.
Put that on the body. Instantly hits through the heart space. Instantly has this. Instantly has this one thing. I don't know.